This lesson is on work, energy, and power, and how they are all related to each other. So, by the end of the lesson, you should be able to identify the relationship between those three things: work, energy, and power. So why do we need energy? So we've kind of been talking about this over the last few days. And remember, energy is just the ability to do work. So that's like, if you're really tired, you haven't eaten anything lately, you don't have a lot of energy to get up and do stuff. You have to eat some protein, eat a protein bar, eat a snack, eat some dinner. Okay. Um, just like you think if you want to do things, you need energy. So let's take a closer look at this word work and what it really means. And so this is going to go down at the bottom of the energy notes that we took the other day. There was that little box on the bottom that had a little bit about work. So we're just going to fill in the rest of that page now. So work is just the transfer of energy through motion. So the key word here is this word motion. So in order for work to actually take place, it means that an object has to move from one place to another. And so when we look at our formula, we have the amount of force put on the object times the distance the object traveled. So for example, in this picture, you can see this, they're lifting the books up and putting them on the bookshelf. So there's a distance, right, that those books were lifted up off the ground. If I'm just holding the book in my hand, technically I'm not doing any work until I move the book. Okay, so here's your formula again. So to make sure you have that written down. And let's look at a practice problem. So it says that the game show contestant pushes the bowling ball 20 meters with a force of 73.5 newtons. So in order to calculate my work, remember it's just force times distance. And so the force was 73.5 and the distance is 20 meters. And so if you multiply that out, let's see, you get 1,470, I think. Sorry, let me grab the calculator. Try to do it in my head, but I'm not so sure. Okay, yeah, that's right. 1,470 would be your answer here. Okay, so all I've done is just plug it into the formula. I'm using the triangle. So here's a second problem. Okay, so we have Carlos raises himself up a distance of 0.8 meters, and his force is 607 newtons. So see if you can plug that in, and then I'll follow right along. And so your answer is 485.6. And then I forgot to say the units of work is in joules. It's a funny word. We just abbreviate it with a J. It's named after someone is where that comes from, but we're not too worried about that. But it is in joules is the unit. So just make sure you're able to do simple calculations like that. So let's take a look at the lab that we're going to do today. So if you're absent and you're watching this video, you're just going to kind of work through the same calculations that we're going to do because you still have to be responsible for doing these on the test. So we're going to talk about power. So in our lab, we're going to have some people that are doing some type of work, and we're trying to measure the power that they're able to do this work with. So we kind of have to answer the question like, what is power? What are we really talking about? So on your, let's see, let me go to it here. On this page here, we're going to kind of start answering that question for what is power and what am I really talking about when I'm using that term. So for our pre-lab questions, let's just go through and write these out. So what is the formula for calculating work? Well, we just went over that. It's the force times the distance. Okay, and I know the definition of energy is the ability to do some type of work. So that means I'm moving an object, or I'm moving, something is moving a certain distance. So power is really just the amount of work you can do over time. So usually if we're saying that something is really powerful, if you think about it, we're almost saying like something is really strong. It can move objects very far, very quickly. And so you have this time component that's kind of being factored into it, right? If I think about two people that are pushing, let's say a huge tire, right? Like an Ironman competition or something, a huge tire across the road, or across like a lot or something. You know, the person who's doing that the fastest, I'm probably going to say, oh, they're a lot more powerful, right? Because that time factor, they're able to do something quicker, the same amount of work quicker. And so we measure power in watts. Watts is our unit, but that doesn't really mean a whole lot to us. So we're going to convert it into horsepower. And so really, in order to do that, 1 horsepower is equal to 746 watts. Okay, so just to kind of give you an idea of what that means, let me scroll down here. So for example, a Honda Civic runs on about 158 horsepower. So that comes out to be about, okay, press my pen. 111,000, almost 112,000 watts, right? But again, watts doesn't really mean a whole lot to us, but just know that the more watts you have, the more horsepower. A moped is only about 2 to 3 horsepower. A horse is about 15 horsepower. Normally, a maximum for humans is about 5 horsepower. That's about how powerful, how much work we can do over time, how powerful we are. So if you look on our activity here, we're actually going to end up converting the amount of work that we calculate in watts into horsepower, so we can just kind of see how much we've actually done. All right, the last question is asking about how would an increase in height, how would that affect our potential energy? And what we know is that height, the greater the height, right, the greater our potential energy. We've talked about that quite a bit. And so we know we have a formula. We don't normally write the G for us, but it's the same thing, is mass times that acceleration due to gravity times height. And remember, G is equal to 9.8 meters per second squared. So all we do is just plug in, you know, our variables for that, right? So let's look at our actual data table. So I have some people, Ross, Rachel, and Joey. They have run basically up a set of stairs a couple times. And I've just measured how long it took to do that. So they moved their body, right? They moved from one place to another. So I know they're doing work because they moved a certain distance. And that distance is the height of the stairs, okay, which is 5 meters. And I timed them. They did it 3 times, and I took their times, and then I got their average time. So this is the time that I'm going to use in all my calculations. Okay, so let's look down here. There we go. And we're just going to kind of start. I'm going to go through Ross here, and then I'm going to let you calculate Rachel and Joey. So if you want to pause after each calculation and do them, that's fine. If you want to wait until the end and do it and just rewatch the video, that's fine. however you want to complete your calculations. I'm just going to do Ross, though, as an example. Okay, so when we're trying to calculate the amount of work done or the amount of power someone has, our mass has to be in kilograms. We know that we in America use pounds while the rest of the world uses kilograms. So we have to convert our weight into kilograms. So all you're going to do is multiply. I have your formula right here. Let me actually get a different color. So maybe it'll like show up a little better. You're just going to convert your mass by multiplying your pounds times 4.54. So I'm going to say 185 times 4.54. Hang on, that doesn't seem quite right. I think I'm a decimal off. Let me double check. Sorry. Where is it? Close your eyes so you're not looking here. Where? All right, I think I'm actually a decimal off. Yep, I am. Okay, so it is not 4.54. It is 0.454. I knew that seemed strange. So let me fix this. I'll say that would be way too much. Okay, so times 0.454. So let me type that in the calculator. 185. So I end up with 83.9. We'll say 0.9. Okay, so that's my mass. Next, we have to get the weight. All right, so weight is just your the mass with the force of gravity that's pulling down on you. So we're going to say it's our kilograms, so 83.9, right, times 9.8. So I end up with, so remember, I'm just going to multiply my answer from the box before, which is pretty much what we'll be doing through this whole thing. I get 822. We'll just leave it at that. We'll just leave it at a whole number since our numbers are getting bigger. Okay, so that's the weight of Ross in newtons. Okay, newtons. So remember, we measured something else in newtons. We measured force in newtons. So what this is saying is that every time Ross takes a step or runs, the force downward that he's applying is 822 newtons. And so when we go to calculate our work, we can just plug in whatever you get for weight as your force. And so we're just going to multiply that times the distance, which again is 5. That's the height of our stairs. So 822 times 5, and that's 4,110. And that's just newtons per meter, basically. Okay, remember now I'm going to calculate my power of Ross. So how much power does he have? How much work did he do over time? So this is his total amount of work, 4,110. And remember Ross, let's see, it only took him 4.3 seconds. So I'm just going to take that 4,110, divide it by 4.3 seconds. And his power is, we'll say, 956 watts. And remember, watts doesn't mean a whole lot to us. So let's see how much horsepower that is. So all we're going to do is take this answer here and divide by 746. So divided by 746. And we get 1.3. Okay, so if we go back to like our PowerPoint here, right? 1.3 was Ross. So we're like a little bit, he has a little less power than a moped, right? Which makes sense. I mean, he probably may not be in super great shape to run up a bunch of stairs. So that's fine. Last but not least, we're going to calculate our gravitational potential energy. So remember, this is just where we're plugging in mass times gravity, which is 9.8. Okay, and then times the height, which is just the stairs. So his mass, remember, is over here. So his is 83.9 times 9.8 times the height of the stairs is 5. So for this one, you're basically just taking your mass. So each person will have their own mass, but you'll multiply them all by 9.8 and then by 5 because the gravity is the same on everybody and the height of the stairs is the same for everybody. So the only thing that will be different is just each individual person's mass right here. Okay, so let's see. Ross's potential energy is 4111, and that's in joules. Okay, and remember we said work is also, this is also joules, newtons per meter. It's the same thing. So you can pause here if you'd like, go through your calculations for everybody, and then we're going to scroll down here and answer some questions. So let's look at number 1. Okay, it's asking what's the relationship between work and power. So let's look here, right? And you'll have a little bit more data than me. But if I look, here's my work. I'll change colors. Here's my work, and here's my power. I'm sorry. Not my power. Power. Work and power. So what you're going to notice, okay, is that you should notice down here with your kind of some of your data. What I'm really wanting to know is like what happens to your power as work increases. Okay, so if your work goes up, what happens to your power? If your work went down, what happens to your power? Okay, so look at your data and just see if you can kind of see, a relationship. If you have only a little bit of work, what kind of power do you have? If you have a lot of work, what kind of power do you have? Number 2, how is it possible for people of different masses to have the same power? Okay, so what we're kind of looking at is, what is the other, if you were looking at power, right, work over time. So the amount of work I do, right, that has to do, my mass can affect that, especially if you think like, if you're the one doing the work, how much you weigh, like your mass that you're carrying around kind of affects, the amount of work that you do. How can someone have the same power output? And you have to think, what other variable is involved in this equation right here, right? So there's a couple of variables that are involved. So what could happen, right? I know I'm talking about power and work here, but like, what about this time? How could time affect, how could that be different for two people and lead them to have the same power? Okay. Number 3, how would this experiment change if you were wearing a loaded backpack? So what variable would that affect, right? How's that going to affect your mass? How is it going to affect your work? How is it going to affect your power overall? Right? Is it going to increase it or decrease it is basically what it's asking. And then what are some sources of error in this experiment? If you're absent, it's probably going to be difficult to do this. But the way that we did this in class is we have, someone is timing each runner with their phone stopwatch. Somebody was measuring the height of the stairs. A couple different people were running up the stairs. So there's a couple different measuring tasks that could be messed up. If you think about how careful were they with their timers, or how careful were they with their with the measuring tape. The last thing, and I guess it's not on this page, but we want to look at is how is work related to the energy, right, of the person or the object, okay, the potential energy. So let's look here. Here's my work, right? And over here is my energy. So what do you notice about those two values? All right, well, we should notice that your work is equal to your energy, which makes sense because what is the definition of energy, right? The ability to do work. So if I have a little bit of energy, I'm only going to be able to do a little bit of work. If I have a lot of energy, I can do a lot of work. So those are usually equal to each other. Okay, and that's going to be important when we go into building our roller coaster, this fact right here. So make sure you don't forget that. This could be a test question. How are these related to each other? So make sure you know that they are equal. Okay, equal work and energy. And I believe that is all for this lab. So once you've got it completed, make sure you